So I'm going to present about the introduction, which is the chemical industry currently faces a critical sustainability challenge due to its heavy reliance on petroleum-derived organic solvents such as toluene and hexane. These conventional solvents are associated with significant environmental and health concerns, which is ranging from high toxicity and severe health risks for humans to the emission of volatile organic compound, which is VOC. To address these challenges, there is a growing global transition towards a circular bioeconomy that aligns with the principle of green chemistry to reduce the ecological footprints of chemical processes. This strategy focuses on replacing finite fossil fuels with renewable bio-based through resources efficient biorefinery models. A key component of this approach is the valorization of waste, which transform agricultural trash into valuable resources, thereby turning potential pollutants into sustainable assets. Moreover, the primary objective of the study is to evaluate the viability of bio-based solvents, likewise bioethanol and D-limonene, as an sustainable alternative to conventional petroleum-derived solvents like toluene. That's all. So,
First, the orange peel were washed, cut into small pieces and dried in the oven to be used as the extraction samples. Next, bioethanol were produced from corn husk biomass through fermentations by using yeast. Meanwhile, limonene and toluene were used directly without further preparations. Then, all of the solvents were characterized by using FDIR to confirm their functional group and chemical compositions. To evaluate solvent performance, the orange peels were extracted by using each solvent and the extraction yield was calculated after the solvent evaporations. Thin-layer chromatography or TLC was also carried out to compare the types of compound extracted by each solvent. Finally, a soil biodegradation test was conducted for 14 days to assess the environmental impact of each solvent.
FTIR analysis was done to identify characteristic functional groups of the solvent used in this project to confirm their chemical composition before extraction experiment. The FTIR spectra of bioethanol, limonene, and toluene were compared with literature data. Only peak position was used because different sources use different y-axis representation. This is important because functional group influence polarity, solvation capacity, extraction efficiency, and environmental sustainability. For bioethanol, the FTR spectrum is shown in Figure 1. The broad absorption band at 3200 until 3600 cm per second represent OH stretching with hydrogen bonding, which is typical for alcohol. This indicates high polarity and strong intermolecular interaction. The bands at 2970 until 2870 cm per second corresponds to CH stretching of the methyl and methylene groups. The band at 1050 until 1100 cm per second confirm CO stretching, verifying the alcohol functioning group. These properties are consistent with literature for bioethanol derived from brewer's Spence grain. The similarity confirms successful derivation and analysis with bioethanol in this project. The highly polar OH and CO group make bioethanol sustainable as a greener solvent to replace petroleum-based solvent. The FTR spectrum of limonene is shown in Figure 2. Strong absorption band at 2953, 2922 and 2850 cm per second are due to CH stretching of methylene group, confirming its hydrocarbon nature. Weak bonds around 3500 cm per second indicates minor alcohol components. The FTR spectrum of limonene is shown in Figure 1. Strong absorption bands at 2953, 2922 and 2850 cm per second are due to CH stretching of methylene groups, confirming its hydrocarbon nature. Weak bands around 3500 cm per second indicate minor alcohol component. Bands between 21600 until 1740 cm per second and 1463 cm per second are related to C double bond O stretching and CH binding vibration. Other small bands represent CO stretching and carbon-carbon bending vibration. This feature confirms limonene as a non-polar terpene molecule. The absence of highly polar functional group explains its lower affinity for polar compounds but high sustainability for extracting non-polar compounds like essential oil. The result matched previous studies, confirming FTR an effective method for identifying green solvent candidates. The FTR spectrum of toluene is shown in Figure 3. Absorption at 3030 cm per second represent aromatic CH stretching, while bands at 2920 until 2870 cm per second indicate aliphatic CH stretching. Aromatic carbon-carbon double bond stretching appears at 1600 and 1500 cm per second, and CH bending occurs at 700 cm per second. This match literature value for pure toluene. The absence of polar functional groups confirm that toluene is non-polar and petroleum-based. This supports the need to replace toluene with greener solvents such as bioethanol and limonene. Overall, limonene and bioethanol support green extractions objective and contribute to sustainable development goals 12. Overall, limonene and bioethanol support green extraction objective and contribute to sustainable development goals 12 through safer and more sustainable chemical process. Next, gravimetric analysis was used to evaluate the extraction performance of bioethanol, limonene, and toluene. The total mass of extract recovered from dried orange peel was measured after solvent removal. This method provides a quantitative comparison of extraction yield but does not show selectivity. The extraction yield are shown in Table 1. The trend observed is bioethanol greater than limonene followed by toluene. Bioethanol produce the highest yield at 25%. Its high polarity allows strong interaction with polar phytochemicals such as flavonoid and phenolic acid, which is abundant in citrus peels. Limonene shows a moderate yield of 15%. This agrees with the literature that reports limonene as effective for extracting hydrophobic and moderately polar compounds such as terpene and essential oils. Although its yield is lower, limonene offers better selectivity and environmental benefits. Toluene produced the lowest yield at 5%. Its non-polar nature limits its ability to dissolve polar phytochemical. This result further highlights its inefficiency and environmental drawbacks.
Hi everyone, my name is Siti Hajar Binti Zakaria, and in this video, I will be presenting the result and discussion of my study. I will focus on the thin layer chromatography analysis and the biodegradation performance of the solvent used. First, I will discuss the thin layer chromatography result. The extract were analyzed using a TSC plate and visualized under UV light at 254 nanometer. Clear bands were observed, indicating the successful separation of UV active compounds. The migration behavior clearly differs between the two solvent systems, showing the effect of the mobile phase polarity. Two mobile phase systems were used. System A is a non-polar system consisting of the cyclohexane and acetone in a 95:5 ratio respectively. System B is a polar system made up of the acetone, methanol, and water in an 85:10:5 ratio. These systems were selected to compare compound migration under the different polarity conditions. In System A, both limonene and toluene extract show high RF value, indicating efficient migration of the non-polar compound. The similar RF value suggests that the compound extract by limonene and toluene have a similar polarity. However, the bioethanol extract remain at the origin due to strong interaction between polar compound and the silica surface. In System B, only the limonene extract show noticeable migration with an RF value of around 0.45. This is indicate that limonene can extract the compound that migrate in both non-polar and moderately polar system. Toluene did not show migration in this system, and bioethanol was not well represented on the TLC under this condition due to its high polarity and limited UV activity. This doesn't mean that bioethanol extraction was ineffective, but rather reflects a limitation of TLC for detecting highly polar compounds. Overall, the TLC results show the mobile phase polarity strongly affect compound migration. Limonene behaves as an intermediate polarity solvent, showing a similar performance to toluene in the non-polar system, but better versatility in the polar system. This supports limonene as a potential green solvent for extracting compound with a mixed polarity. This slide shows the visual appearance of the solvent-treated soil sample after 14 days of the incubation. Compared to the initial condition, the soil becomes drier and lighter, indicating biodegradation. However, the extent of the drying varies depending on the solvent used. Soil treated with a bioethanol become almost completely dry, indicating the rapid biodegradation. Limonene-treated soil retained some residual liquid, suggesting the slower degradation compared to bioethanol. Toluene-treated soil remained the wettest, indicating slower removal and greater persistence in soil. Bioethanol exhibits the highest biodegradation efficiency at 99% after 14 days. It is readily metabolized by soil microorganisms as an easily available carbon sources, resulting in the almost complete drying of the soil. This indicates a low environmental resistance and a high biodegradability. Limonene shows a high biodegradation efficiency of 96%. It is a moderately polarity and bio-based origin support microbiome degradation. However, some residual liquid remain. This is indicating the slower removal than bioethanol. Overall, limonene demonstrates a good biodegradability with a moderate soil persistence. Toluene recorded the lowest biodegradation efficiency at 70% after 14 days. This result indicates the bioethanol and limonene are viable alternatives to toluene. Both has higher biodegradability, lower environmental persistence, and reduce the soil contaminant risks. As the renewable bio-based solvent, they support the green chemistry principle and align with the Sustainable Development Goal SDG 12 on a responsible consumption and production.
Conclusion, this study demonstrated that bioethanol and D-limonene are effective, environmentally responsible for alternative to the petroleum-derived toluene for extracting bioactive components. While toluene showed limited efficiency for polar consistence, bioethanol achieved superior yields to the higher because of its higher polarity. And D-limonene displayed selectivity across non-polar to the moderately polar components. Both biosolvents exhibited significantly higher biodegradability, which is 96 to 99% compared to toluene, which is 73%, aligning perfectly with green chemistry principle. Moreover, to facilitate broader industrial adoption, future efforts should focus on scaling up production through pilot-scale biorefinery models and conducting comprehensive techo-economic and life cycle analysis to ensure economic viability. It's recommended to optimize extraction protocols through parametric studies and investigate hybrid extraction method that integrate biosolvents with existing industrial processes. Additionally, future research should expand the scope to these tests other biosolvents such as 2-methyl tetrahydrofuran using advanced technique like microwave assisted extraction, while also developing standardized assessment tools that weigh technique performance against environmental conclusion. This study demonstrated that bioethanol and